In Washington, the U.S. Department of Commerce is actively evaluating regulatory measures to restrict federal procurement of advanced Chinese AI models. Meanwhile, in Beijing, China's Ministry of Commerce is holding parallel consultations to prevent domestic frontier models from ending up in Western hands. The specific asset triggering this synchronized anxiety is Kimi K3, a multimodal frontier model built by Moonshot AI containing 2.8 trillion parameters. Chinese regulators have spent weeks consulting domestic industry leaders like Alibaba, ByteDance, and Zhipu to discuss how to tightly control these technology transfers. Two rival superpowers are simultaneously fighting to restrict the exact same asset. The US wants to keep it out, China wants to keep it in. That friction points to a complete breakdown in standard technology policy. To understand why traditional bans are failing, we must look at how these models are distributed. Typically, a user accesses a frontier model through an API, or Application Programming Interface, which acts as a secure gateway to the provider's servers. Operating through an API means the provider retains total control. They can monitor every prompt, throttle request volumes, or completely shut the valve to geo-block specific users at any time. Moonshot AI chose a different path for Kimi K3. They are releasing it as an open weight model. Open weights mean the raw, trained parameters of the neural network can be downloaded directly as a standalone file and run on a user's local infrastructure. Once that file is transferred, the connection is severed. The provider loses all ability to monitor queries, restrict access, or switch it off. It is a permanent, non-retractable transfer of technology. Traditional regulatory frameworks rely on choking off access points, but open weights eliminate the access point entirely. Inside that downloaded package is a massive architecture. Kimi K3 contains 2.8 trillion total parameters. Processing a dense model of that size, meaning every parameter is activated for every single word generated, is computationally and economically impossible for current hardware. To make this scale functional, Moonshot relies on stable latent MO, a sparse mixture of experts architecture, divided into 896 expert nodes. Rather than running the entire grid, Kimi K3 employs extreme routing sparsity. For any token passing through, it illuminates exactly 16 specific nodes, leaving the rest inactive. The system manages this high sparsity using quantile balancing, which smoothly distributes the computational load across all the active nodes without needing constant heuristic updates. By only activating a tiny fraction of the network at a time, this extreme sparsity bottlenecks the raw compute required per token, allowing a 2.8 trillion parameter model to operate efficiently while maximizing its reasoning capability. Kimi K3 pairs that processing efficiency with a natively multimodal context window capable of ingesting up to 1 million tokens of data at once. Naively processing a sequence of 1 million tokens from scratch for every single query causes immediate computational ruin, completely overwhelming memory bandwidth. To bypass this physical limit, Moonshot implemented architectural changes known as Kimi Delta Attention, or KDA, and attention residuals. KDA utilizes pre-fill caching. Instead of reprocessing long, repeated instructions or massive documents with every new turn in a conversation, the model stores and injects the previously processed representations. This chart shows the real-world economic impact of that engineering. Looking at the Bifrost API pricing for Kimi K3, a standard uncached input costs $3 per million tokens, but an input served from a cache hit costs just 30 cents, a 90% reduction.
KDA pre-fill caching is the exact engineering breakthrough that makes massive context reasoning economically viable for enterprise applications. Software logic only solves half the equation. To understand the true barrier to entry, we have to look at the model's physical deployment limitations. During training, Moonshot utilized quantization-aware techniques to compress Kimi K3 into the MX-FP4 standard, allowing the weights to operate at 4-bit precision. Even with aggressive compression, the math is punishing. 2.8 trillion parameters at 4-bit precision yields a 1.4 terabyte block of raw weight data. Once running, this footprint expands to accommodate massive KV cache and activations, overflowing the memory capacity of any single GPU on the market. Because of this, Moonshot explicitly warns that production deployment of Kimi K3 requires a distributed supernode topology utilizing at least 64 connected accelerators. The idea that open weights means anyone can run this model on a laptop is an illusion. Downloading Kimi K3 is an enterprise-scale technology transfer that demands millions of dollars in physical infrastructure to operate. This brings us back to the geopolitical tension in Washington and Beijing. The exact moment that 1.4 terabyte file is officially published, the regulatory window closes. The weight file instantly duplicates endlessly across decentralized repositories. U.S. procurement bans fail in this environment because domestic federal contractors can simply download the files independently and self-host the Chinese AI architecture on their own servers. Conversely, Chinese export controls fail because they cannot act retroactively. Once a decentralized file leaves their borders, it is mathematically impossible to recall. Because software is infinite and respects no borders, applying digital export controls to an open weight model is functionally obsolete the second it launches. But while the software code can be duplicated to infinity, the enterprise hardware required to actually execute it cannot. The absolute requirement for a 64 GPU supernode creates a hard physical bottleneck for any entity attempting to run Kimi K3. High bandwidth interconnects and massive accelerator clusters consume vast amounts of power and require highly specialized data centers. They are highly visible and nearly impossible to procure covertly. To enforce AI policy, regulators must shift their focus entirely from the digital weight files to the raw silicon and to the physical hardware supply chain itself. The regulatory battleground for frontier AI has permanently moved. Governments can no longer waste time trying to police infinite code repositories. They must audit the highly constrained physical infrastructure that makes the code run.